Right. So, as I just said, this is our ECCV 20 paper, and the topic is instance association in multiple camera views. So what exactly this means? As we have been developing deep learning algorithms throughout the years, and we gradually realize that most of our algorithms are actually working on single camera or monocular cameras. And there are some use cases. For example, let's say we want to monitor a basketball court, and we want to mount, set up several cameras around the court, so we can have like a holistic understanding of the entire thing. Or rather, we have let's say a smart refrigerator or some like enclosed space where we want to monitor the items in it using multiple cameras. Then the problem arises, that is, how do we associate objects from different cameras? Let's say we have multiple cameras, and in each of the camera we have detect multiple objects. How do we associate them across the cameras? So we actually developed a data set called MessyTable, and along with some baseline algorithms. And this is a joint work between SenseTime Research, the company I'm working in. I'm currently a researcher, and also with my friend Junzhe from Nanyang Technological University. And he will be, after this talk, will be give you another talk on unsupervised point cloud completion. Right, so without further ado, let's dig in. Right, okay, let me put it here. Right, okay, so as you can see, this is an example of the data set we have in the MessyTable. And it is indeed a MessyTable, right? And we are showing, we actually have 9 cameras around manually set up table, and we are showing 4 of them. And we can immediately see that the table is pretty messy, and this is our purpose. We actually purchased many merchandise or products from the supermarket and from maybe IKEA just to set up a realistic dining table. And we actually have a group of data annotators and collectors, and we are giving instructions such as we want to make the tables as realistic as possible, and such that we can include all the real-life problems in our data set. So first problem that comes to mind, and also quite common for you guys if you are working on multiple cameras, is the large angle differences. So for example, if we are observing an object from one angle, let's say this can of tuna, if you are looking at the camera from the top view, it's like it appears to be something hard to describe, but pretty different from if you are observing it from other angle views, other angles, right? And so this is becoming a big problem, and we actually run experiments on it to show that large angle differences are causing problems. And also occlusion. There are some more examples in the data set. We can see that the sub-figure A, there are 3 apples, and they are visible from one side of the camera. However, if we're observing the thing from the other side, the apples are actually occluded by this cardboard box. And there's another apple that's in sub-figure B that's even completely invisible from another view. So we use a dotted line to represent it. And then also, I'm sure pretty of you are working on the field of ReID, and one prolonged problem with ReID is that there are many people wearing similar clothes, or they appear to be similar, or they are twins to begin with, and this is causing the problem called similar or identical looking instances. And we also include these challenges in our data set, so you can see that sub-figure C and sub-figure D. In each of the subfigures, we are actually having multiple products of the same type at the same time present on the same table, and just observing them from different angles, right? This is causing also a lot of problems. And also, this is quite specifically related to general objects, because we don't normally see people stacking up. But right, for objects that's on a table, especially a messy one, they are very common to. It is very common for us to find objects that are stacking up together, or they are not placed on the flat surface of the table, maybe on an elevator surface, such as on a cardboard box. So why is this important? Because many of you may know about homography. Homography is actually taking advantage of the assumption that there's a common plane inside the field of view, and it's shared. This common plane is the vision of this plane is actually shared among all these cameras. So with this constraint, we can actually simplify the problem of multiple camera association. We can just use, let's say, project a point on this plane, and we can have the homographic projection matrix to project this point from this angle, from this camera to another camera. And this projection is not ambiguous, and it will simplify the problem a lot. But in real life, this is not a perfect world, and we can see that if the objects are stacked up or they are placed on elevator surfaces, we cannot use homographic projection. And we will show more in the experiments. Right, so more about the MessyTable, the dataset itself. So there are a lot of multi-view datasets out there. For example, MPI multi-Kinect. This is a pretty old dataset where Kinects are set up in a keychain, and there are also multiple objects placed on the keychain in the keychain on the dining table. Right. So, but the problem with that is it's a pretty small dataset, and you can see there are only 32 things and a couple of hundreds of images, and it can hardly be called large scale, right? And there's also an EPFL multi-view, multi-class dataset. It was developed by researchers at EPFL, and it has 3 classes: people, cars, and buses. So it is a newer dataset, but the problem with that is still it cannot be applied to general objects, and the dataset itself is still quite small. And then after that, there's WildTrack. WildTrack is a really brilliant dataset, and it actually has multiple 7 cameras, in fact, set up at a station, and we can use this camera to observe the crowd from multiple angles, and it can be used for tracking across the camera. However, the problem with WildTrack is it only has 1 class, which is human. So if we want to extend the research towards general objects, or rather to lay a fundamental research, we will probably recommend you guys to use MessyTable. And we actually divide the things in MessyTable into 3 difficulty levels. So easy being pretty simple. As you can see, there are very little occlusion, and the number of instances are quite small. And also medium followed by hard. As you can see, the hard is really challenging. And when we were designing and developing this dataset, we tried to make it challenging. So it cannot be saturated easily, and it can serve the community for a longer time. And for subfigures B to D, let's look at B first. So we actually run statistics on number of instances in each of the difficulty levels, and we can find out that the hard things are containing more instances, which is making sense, right? The more instances they are, the things tends to be harder. And also there are fraction of overlapped instances. So what does this mean? If an object can be observed by 2 cameras at the same time, we call it overlapped. So there are some overlapped field out there, and the objects are inside this overlapped field of view. We can see over here, right here for easy, most of the objects are actually commonly observed by all the cameras, but in harder subsets, there are fewer and fewer objects that are simultaneously observable from all the cameras. And also we are adding more identical instances just to add some spices into the subset. As you can see that the hard subset are containing more identical instances, which makes the association task even more challenging. And we have 9 cameras, and we try to simulate the real world by randomly placing the camera positions and angles. As in subfigure A, there's a scatter plot of all the camera positions we have in our data set. there are total 567 setups. In each setup, the camera angles and positions are fixed. Then we can collect a few scenes. We call it scenes. Each scene is arrangement of all the objects on the table. So we have 567, and we have 9 cameras. So this gives us over 20,000 relative camera pairs. So you can see that here is a pretty rich distribution of camera angles as well. As you can see, we are varying from, let's say, 5 degrees to almost over 120 degrees in the distribution of relative angles between cameras are showing that there's some diversity over there. Right, and another key feature of MessyTable is that it contains general objects instead of, for example, a few classes, humans, cars, and buses. We are collecting 120 classes to be exact, and you can see here we divide all the objects into supermarket merchandises, such as like chips and bottles of beverages, and we have agricultural products. I think that it's actually vegetables and also fruits. And we have bakery products, breads and buns, things like that. And the dining wares, because we cannot do without our silverwares, right? We need our forks, our plates to hold our food. So right there, we also include those dining wares in the set. And here is a photo of all the objects we have in the data set. As you can see, this consists of objects of varying sizes, textures, materials, and everything is varied. And we try to add diversity inside the data set. Okay, so is there any questions at this moment of time? Otherwise, I will be going through methods we developed as baselines.
From my end, no, very clear for now. Thank you. I didn't see anything in the chat also.
Right. Okay. Let me continue from here. Right. So how do we perform multi-camera association? The key idea or the key frame is like this. So let's say in view number 1, we observe 3 instances, and in view number 2, we also observe 3 instances. And there are many methods we can use to actually compute the similarity score between instances across a camera, and we can make this a distance matrix. So for example, I have a super brilliant idea, and I implement it, and I can compute the distance between the green square to be 0.1, and let's say the distance between the blue circle to be 0.1 as well. And also I can fill up this distance matrix by computing the relative similarity scores. And I can run KM or Hungarian algorithm, as many of you guys know about. This is the bipartite matching algorithm, which is quite developed, and we try not to use deep learning in every step, because this step is pretty clear, straightforward, and clear cut. And also after we apply KM, we can obtain the binary results, whether the instance A in view number 1 is associated to instance B in view number 2. And also we will be running some thresholding, because even after running KM algorithm, we find out that there is potentially a match, but because it is a global optimization process, and there might be matches with very low similarity scores. So we will also get rid of them, and so by that we perform thresholding, and we get this thing called adjacency matrix. This will reveal the association status or the output of our pipeline. So if it's 1, meaning these 2 objects are associated from 2 camera views. If it's 0, meaning they are not associated. So as you can see over here, the green squares are associated across the views, and the blue circles are also associated. But the red triangle and also the yellow diamond are not associated to any.
There was a question on the chat. Actually, I also have one. So Alex asked, Did you generate ground truth boundary boxes? Manual? I think you meant how did you generate ground truth boundary boxes? Was it manually annotated?
Correct. I think we are going to that part pretty soon, or have already passed it. All right, over here. So you can see here we have over 1.2 million bounding boxes, and across all the 50,000 images and 5,000 things and 500 plus setups. Yes, we actually manually annotate them. So we actually employed a group of about 20 annotators. So we have them undergo a tutorial how to perform the instance association. So the steps are like this. We didn't include this in the main paper because it's pretty tedious and there are many steps. So Junja and I have been working on this for over 8 months just to get the annotation pipeline working. All right, so the steps are like this. So the annotators are first asked to annotate the bounding boxes by saying that they are supposed to annotate everything, all the foreground objects in the scene. Then after all the objects are already annotated, we have the bounding boxes. Our tool will ask the annotators to associate them. So for example, okay, I don't have the annotation tool inside these slides, but I can briefly tell you how it performs. So as an annotator clicked on the bounding box in one view, he or she will be asked to click on the corresponding bounding box in other views. So after he clicked on all the cameras, and there are some cameras, maybe this object is invisible, so he or she can skip that. The bounding box association annotation is completed. So there are two steps. First will be bounding box annotation, and second will be association. So there are 1 million bounding boxes. All of them are manually annotated.
Well, this is impressive work. Just the numbers themselves, really amazing.
Right. So we truly hope more people can get to know this work and use it in all various applications. Right. Okay. Let me continue from here. All right. So just now I talked about the framework, right? Then comes the important question: how do we actually evaluate the performance of multi-camera association? So we are actually proposing a new metric called IPAA-X. So what does X mean? X means how % of the objects are correctly associated in one scene. So we provide examples here. Let's say we have, let's look at the top left corner. We have two views. There's a predict adjacency matrix, but obviously there's some mistake, right? The blue circle from view number 1 is actually associated with the yellow diamond in association 2. So it definitely it should be penalized as compared to the ground truth adjacency matrix on the bottom left. So how do we run the evaluation? We actually first count the number of correct the true positives. So on the first diagram, we count the one between the two green squares as correct. And on the right, we actually count the number of false negatives and false positives as because the blue circles are not correctly associated, where in contrast, the blue circle is from view number 1 is actually associated with the yellow diamond from view number 2. So here is a false negative and a false positive over here. And
we don't see your pointer. We don't see your mouse pointer, by the way. I forgot to mention. Maybe now we do.
Right. Let me figure this out.
Oh, yeah.
Can you see my mouse?
Yes, now yes.
Okay, right, cool. Yeah, this is better. Okay, thanks for the suggestion. Right, over here you can see that first here is a false negative because here's supposed to be a 1, and here's a false positive because here's supposed to be a 0, right? And over here it's correct because the red triangle is not supposed to be associated with anybody. So this part is correct. And over here, here is a false positive because for the yellow diamond, there's a false positive association. So we have the ground truth, right? We know there are 4 objects inside the scene. So over here we see that only the green square and also the red triangle are associated correctly, so there are no mistake at all. And this will tell us that only 50% of the instances are correctly associated. So let's say we are calculating IPAA 90. That means we are counting things that with more than 90% of the instances correctly associated. This thing will not be counted as one. Okay, so we're going to introduce a few metrics: IPAA 80, IPAA 90, and also IPAA 100. So each of the things, let's say a thing is having 80% of the instances correctly associated, it will be counted towards IPAA 80, but not be counted towards IPAA 90 or IPAA 100. I hope this part is clear, because it's a bit confusing, right? And we try to make it clear by drawing all these toy examples. Okay, cool. We come to the baselines. Right, so homography. I'm not sure how many of you are working with homography. So homography is basically, let's say we're going to have a tabletop, which is visible from multiple camera views. And let's say I point, I mark something. Let's say if I can, is it possible for me to draw on the screen?
It should be. There is this option. I always don't find it, but it should be. Let's see.
Okay, right. Okay, I see. Over here, cool. Laser pointer, there's no pen. Right. So let's say we have 2 cameras, right? So this triangle is a camera, and we have a plane, which is a common plane. So this camera is able to view this part, and this camera is also able to view this part. So actually, this simplifies the multi-camera association problem, because we have additional constraint, which is the table, right? We know the line coming out from the camera plane will going to intersect with this plane. So this additional assumption actually help us to simplify this problem. So let's say we in this camera we observe X, right? So it's here, X. And in this camera, we also observe X over here. And the transformation from this camera, this X to this pixel coordinate to this pixel coordinate can be achieved by using a homographic matrix, which is a 3x3 matrix. And there's no ambiguity over there. So once I get this H matrix calibrated, all the projection from this camera to this camera will be unique. There will be no ambiguity at all. So this is what we call a homographic projection. But the problem with homographic projection is that we need to have a common plane. And this assumption does not hold always. So right, so here we actually run homography, and you can see the results fails terribly. And even for the more strict IPAA metrics, we are giving 0 the performance of homographic projection. But this is understandable, because as we said, the MessyTable is pretty challenging, and there are many objects that are stacked over each other, and also there are objects placed on elevator surfaces. So this makes homographic projection not working. And also SIFT. So before deep learning comes out, and probably even until now, we are using SIFT. So how does this method work is that we actually extract all the key points and their features from the first bounding box from one view, and then we also extract the features from the second bounding box of another view. Then we try to associate these 2 bounding boxes using the SIFT features. But in real application, we realize that the SIFT is not robust enough, because it's a manually designed, handcrafted feature descriptor. So it tends to cluster around feature-rich regions, and those regions with very little texture or repetitive texture is going to have terrible performance with SIFs. So with that observation, we actually introduced three sets of deep learning based patch matching baselines. They are existing works over there. And for each work, we actually provide two variants. One is the variant which we reproduce using from the original paper. And the one with a star is actually we replace the backbone with something better. So let's say the original work is using a backbone that equivalent to ResNet 18. We're going to replace that with ResNet 50, let's say, just to make the backbone stronger. But we can see that the results are quite poor still. So all of them are actually, all the previous three baselines are using the Siamese architecture. So we see, oh, Siamese is not enough. How about let's try a triplet. Yeah, so we implement a triplet net baseline that uses the triplet loss, which is quite famous if you guys are working on fields such as unsupervised learning. Right, we implement a triplet loss. And we realize that the results are improved by a lot, but still not enough. Let's say we look at IPAA-100, they are merely about 6.8% of the things are correct, are fully correct. So the ZO actually means zoom out. We will tell you more about why do we actually implement this feature in the later section. But after that, we'll be talking about the baseline we actually introduced. It's called ASNet. So ASNet, what does this stand for? It stands for appearance and surrounding. So in our practice, we realize that if we only look at the object itself, it's not going to help because there are a lot of identical objects, and the features that are coming out from the object itself may not be that informative to tell us the correct association. So we need to look around, right? And this is what we call the surrounding feature extractor. So this is really a baseline, and we are really hoping the community can be developing fancier methods over it. So first of all, we will have the appearance feature extraction branch. Over here, we're going to use deep learning backbone to extract the features of the object itself. We call it VA, then appearance, right? And also here we have view B, we call it VB appearance. So these are two feature vectors. And for the surrounding region, we actually mask out the object itself and ask the network to extract feature from the surrounding region. And we're also going to have two sets of extracted feature vectors. And we're going to compute the L2 Euclidean distance of the appearance feature as well as the surrounding feature. So I have two sets of distance, which one coming from the appearance of the object itself, and also one coming from the surrounding area. Then the problem comes: how do we actually fuse these two distances? Are we going to fuse it manually? Are we going to design a hyperparameter that's going to just like a weighing factor just to fuse them? Instead, we actually develop a new distance computation. We use cosine similarity to compute how similar the appearance features are for the two objects. So the motivation is actually quite simple. If the lambda is very high, then meaning that the objects are pretty similar to each other. So if two objects are very similar to each other, we cannot differentiate or associate them by looking at the object itself. We have to look around, right? So this will provide a higher weightage to the surrounding feature extractor and also the L2 Euclidean distance between the surrounding features. So right, this is how we actually design the network to dynamically adjust the weightage between the appearance and the surrounding feature extraction, and to achieve the better results. Right, we can see over here the ASNet is outperforming all the baselines we have be it the classical ones and also the deep learning ones, and also a strong baseline we developed for triplet net, we developed for triplet loss. Right, and also it's time to go back to zoom out. So what does zoom out mean? Zoom out actually means we are going to crop a bigger area. So in ASNet, right, we actually have two branches of feature extraction. Then the surrounding feature extractor actually only extracts the surrounding area. We actually mask out the object area itself. So over here, the zoom out technique does not perform this. It just expands the receptive field, or it just expands the bounding box by a certain ratio and fit this crop into the feature extraction. And the ASNet are using a two-branch architecture. We can see over here, ASNet actually forces the network to look at the surrounding area. And for zoom out, we can see all the for the neural network activation are concentrated at the center of the image of the crop. But for ASNet, also there are some attention around the object itself at the center. For example, in this case, we can see here we are trying to associate the orange, and here we have a box of milk, and the attention is actually placed on the box of milk. Whereas if we only apply the simple zoom out, the attention is still focused on the orange itself. So it does not achieve our goal. Right, so we have here an additional technique called epipolar soft constraint. So previously we talked about homography, and the epipolar constraint is also a pretty basic knowledge in computer vision. That is, we know that, okay, drawing time again. Okay, let's say we have a camera over here, and we see something over here. So this is what the camera sees. In fact, in the 3D world, it's not a dot, it's a line, correct? So for here is a camera number 2. What camera number 2 sees is actually a line instead of a point. So this is actually the reason why we are saying that 2D vision is ambiguous, because it does not have the depth component in it. So we actually compute the epipolar soft constraint as the distance of the object to the epipolar line from another camera view. So this will add additional constraint into the association. The motivation is pretty simple. Let's say the object is very far away from this line. It's very unlikely that these two are going to be associated. So this epipolar soft constraint will add additional penalty to those cases. Right. Okay, so we have developed ASNet, and we are achieving some good results, reasonable good results. And over here, what are remaining problems we realized inside during our development of ASNet? First of all, will be difficult things. So we have the hard subset, and a lot of things are pretty difficult. We will elaborate later. And the large angle differences, because when we have 9 cameras and they are more often than not, the 2 cameras are viewing the scene from very different angles. Right. So we actually run a test on each of the subsets, the easy, the medium, and the hard. We realize that when the set gets more difficult, the results is getting worse, which is making sense. And also, when the camera angle is getting the camera angle differences are getting better, getting larger, the performance of all the baseline methods actually become worse. So this we are evaluating the results using 3 metrics, and for FPR 95, the metric is the lower the better. So the network still are performing much worse when the angle is becoming larger. And there are more failure cases. For example, there are heavy clutter. All these bananas are placed together in very closed arrangement. It's very difficult to associate them correctly. And also, if the camera angle so happens to not be able to observe due to occlusion, not be able to observe the object, the association is going to be pretty difficult because first, they are having pretty similar appearance feature. Second, the surrounding features are also quite similar because they are stacked together. Third would be the epipolar constraint does not work here because they are very closely placed. So there are three research directions we find worth further investigation. First will be, how do we actually extract stronger appearance, surrounding, and geometric cues? So this our ASNet is definitely not good enough, and we encourage more people to follow MessyTable and to spend more to develop better or stronger models and methods for instance association across multiple cameras. And the second, we in ASNet we develop a dynamic way to compute the weighting factor lambda, and but are there even smarter ways to fuse these cues? I believe the answer is yes, and we just haven't come across it. And one day somebody will come up with a better solution to fuse these cues. And the third, I think this is even more important. Are there information that we have using? For example, we are using appearance, we are using surrounding, and we are using geometric information. Geometric information as in the soft epipolar constraint. But are there going to be other information that we haven't been using, which is critical to the problem of instance association across cameras? Okay, just a little bit add-on on the MessyTable itself. So we designed the MessyTable to serve two purposes. First being a benchmark, a good benchmark, an indicative benchmark, such as so as to achieve the purpose that a good method that performs better on MessyTable also performs better on other multi-camera datasets. And also we want MessyTable to serve as a training source. So pre-training on MessyTable will make the network pretty strong already for multi-camera tasks. So first will be the indicative benchmark. As we show here, the methods that performs well on MessyTable will be likely to perform well on other multi-camera datasets. And also, if we pre-training a network, not in ImageNet, which is a common approach, by using MessyTable, we are getting better results on the three multi-camera datasets. Right, and I believe, yeah, you guys, if you are interested and to learn more details, you can click on this link, and we have a project page set up, and you also download the data, as well as there's a link to our GitHub page. We are constantly maintaining to for instance association in multiple camera views. Right, with this, I'm happy to answer any questions.
You are on mute.
Right.
Yeah, we have questions. Actually, we had for before, but we waited for the flow to finish.
Right.
So Sol was asking. I hope I will understand the questions right. Sol is asking, how did you use bipartite matching when the number of objects is different between views? It's our first question.
Okay, right. So let's jump to the. So the algorithm will leave out the unused ones. By saying that, okay, drawing time again. Let me find my pen. Let's say we have three objects right over here. This is from, let's say, one view, and then we have two from another view. So we didn't observe the third object from the second view. So what does the KM or the bipartite matching algorithm going to do is going to match these two, and because this is going to match to nothing, it's going to be leave out. So only two association will be established. Okay, this part is not deep learning. This is like a classic algorithm.
And the second question is, how is the distance calculated? Was it the closest points, single leakage, centers, etc.? So that question, I'm not sure I'm understanding fully.
Okay.
Sol, are you here with us?
Yes. Can you repeat the question, please? I didn't get it.
Yeah. No, yes, we will wait for her to maybe write something. In the meantime,
Okay, can you hear me now?
Yeah, yes. Yes, please go ahead.
I think there's a problem with my...
Okay, I think her mic.
So just write it down for us, and we're like as elaborate as you can. In the meantime, there's a couple of more questions. So
I think I understood the Sol question. I think it's meant that it's a distance of similarity, not distance of geometry. As far as I understand the question.
Okay, distance of similarity. I assume it's talking about this page.
I meant the matrix, the arrows. What?
Oh, over here.
This one is the distance matrix of similarity distance, right?
Sorry, pardon me. This is the distance matrix. So the lower the two objects are, they have a higher tendency to be associated. So you can see here, this distance, those with smaller distance are associated. Sorry for this part.
What's the calculation method there?
Over here. So this is a general framework. So over here you can use any method. So all the baselines we are actually developing comes to this part. So after we compute the distance matrix, everything is standard. So we're going to run KM and the thresholding.
Can you maybe rephrase the question? Why do you have a 0.8 between green square and blue circle and 0.9 between green square and yellow? Yeah. Why it is 0.8 and 0.9? Right. What's the difference?
Yes.
Okay, so the network works like this. So let's take ASNet, for example. So ASNet, okay. So for each of the instance, you will go to ASNet. Then ASNet will give me a score, say, or rather distance, and put it here. And so over here, we're going to we're going to fit this green square and this blue circle in, and it will give us a second score. So so let's say we have n objects, there are going to be n square computations, and to fill up the entire distance matrix. Then we can perform Kn and thresholding to obtain our adjacency matrix. So this is the general framework, and all our innovation or the community are going to work at is the various methods to extract better distance. So just now we are developing ASNet or epipolar soft constraint or even homographic. Everything can be abstracted into distance computation. So that's why we find this is a good framework to perform multi-camera association. Yeah, I hope this answers the question.
Yeah, for me it did actually. Yeah. Okay, Alex, you had a question. You go ahead, ask yourself maybe.
Okay, thanks. Thanks. Quite interesting talk. So I had a couple of questions. First, on what data you evaluated the models, like the models that you showed and your model. So is it does it has in the evaluation data same data that you use for training? Does it have same camera positions, same domain, or did you try to evaluate it on completely different new objects in different domain in different camera positions? Okay,
thank you for the question. We actually divide the data set into train set and the val set, and also a test set. Right, so we kind of uniformly distribute all the data. So the 120 object will be present in both set and also test set, and also the camera configuration. However, the camera configuration can be in either train set or val set. So one configuration will not be seen in training as at the same time in testing. This is not going to happen. But the objects are definitely shared because we are not working on, let's say, few short object detection. For those kind of topic, maybe we need to leave out, maybe have a small set of objects that's unseen in the training.
Okay, that answers question. Thank you. The one more is how do you see practical application of the network? Should be something like we first run it on 2D detection model, then we compare each box predicted from the first image with a box predicted with second image and find similarity. So should be a sliding window or something else? And as a part of a question, what is performance of the network? How fast is it?
Okay, I'm not sure where I get your question correctly. So first part will be what kind of like real world applications like we can be using the ASNet for? Is that correct?
Yes. So basically, you get two images from two cameras. We want to find same objects on from these two cameras. We don't have any boundary box. We don't have any. We just have two images from two monocular cameras from different places, from different views on the same place. What would be next steps?
Okay. Right. So as you say, we have two images, right? Let's say we're going to have a square, and we want to know how many people are there. So for each of the view, we are going to observe only part of the square, right? Correct. And there's no way we can count how many people are there on this square. So with our multiple camera association, we first perform detection on each of the image views. So let's say I detect 3 people, I detect 4 people over here. Then we run the instance association. We find out that there are 2 people commonly observed by both sides. So 2 plus 2 plus 1 are okay. We find out there are 5 people on the square. And if we are not using a multiple camera system, there's no way we can come to this conclusion.
Okay, so it means that you run it for each box with each box. If you have n objects detected by 2D object detection, okay, so it's n square.
Correct. So it's n square. Yes, correct.
And what is performance of the network? How fast is detection of comparing of 2 objects?
Yeah, I think we got asked about this question in our paper submission, and one of the reviewer actually raised this question. I need to consult Ginger for 1 second. Do you remember the network performance speed?
It's less than 100 milliseconds.
Yes, correct. Because if your n is not like crazy, it's not like 10,000 people on a square. Normally we are looking at about thousands of objects instances on in the same scene. So the network running time is below 100 milliseconds.
And the
KM is super fast.
Yeah. So let me just add on. Actually, we are only computing. For example, if you have n views, and for each view we have m objects. Actually, we have only n times m retrieval of the features. We do not need to basically the time complexity is not n square, and only the KM method the KM algorithm is with time complexity of n square. Yeah, so it's pretty scalable. Okay, and another thing that I'd like to comment is currently the multi-view object detection and our framework are disentangled. So basically they are separate stuff, and we are using off-the-shelf multi-view detection frameworks, basically object detection frameworks, and then using the extracted bounding boxes to do association. And we actually do have the environment using off-the-shelf instead of the ground truth bounding boxes. And we believe that comparing both the multi-camera detection as well as the multi-view association jointly end-to-end will be the future direction. Yeah.
Correct.
Okay. Not sure if, yeah. So just to reiterate that the feature extraction is n, and only the assumption part is n square, which is super fast because we're using a classic algorithm.
Okay,
Thank you.
Everybody's on mute.
Okay.
I think we finished the first part, and guys, let's have a 5-minute, really just a 5-minute break, okay, for everybody to refresh, and we'll start the second part. Is that okay?
Cool.
Yeah. Good. So we will see everybody. This is like around time now, so we'll see all at 05. See you guys soon. I'm turning off my video for a sec, and I'll be back soon. Yeah. In the meantime, there was a question here. I see everybody's on board. So in the meantime, there was a question here. Does this work with traffic cameras too, or the distant matrix with the shape texture of the vehicle confuses it?
Thanks for the question. It definitely works with traffic intersections, this kind of setup. Right, I think the question about the texture is exactly the challenges that we want to overcome. Let's say how do we extract a good picture to for computation of a good dense metric. Yeah, there are definitely challenges, and the general framework can be applied to traffic cameras as well.
Junzo, I think we could start your part now.
Okay, let me share my screen.
And I would never have believed I would do something at 3 a.m. my time right now.
We really appreciate it.
Huh?
We really appreciate your time.
No, I'm amazed that I'm able to keep focus. That's what's it means that the talk is good, by the way. It means that it's very engaging.
Okay. Can you guys see my slides now? Okay,
yeah.
Then maybe let's start. Welcome back. My name is Junzhe, and today I would like to share about the unsupervised 3D shape completion through GAN inversion. So when we're talking about shape completion, we're talking about in the form of point clouds. I believe many of you are in the autonomous driving industry, and you should be very familiar with point clouds, so no need to give more background. So
recording. Don't record.
Sorry?
Is this session recorded? Someone in the chat is asking.
Hi, Peter.
It's recording. It have never stopped recording. No worries.
Okay, good.
Thank you.
Okay, just let me basically introduce about the teams. So this work is a collaboration between Nanyang Technological University S Lab and SenseTime, as well as the Shanghai AI Lab. Okay. Now let's basically start with a brief introduction on point cloud completion. So when we're talking about shape completion or 3D point cloud completion, basically given a very partial or sparse shape, then we aim to estimate or hallucinate the complete geometry of this partial shape. So in many scenarios, sometimes they mimic the real world scans. For example, the KT dataset, and then we have the virtual partial scan. And sometimes we want to mimic the occlusion, and we have the ball hole incompleteness or part level incompleteness. Okay, and I believe point cloud completion is getting more and more popular and essential for downstream tasks such as robotics navigation or scene understanding. Okay, and as of now, most of the existing frameworks are trained in a fully supervised manner with paired partial and complete data. And particularly, they are only from one particular domains, for example, either virtual scan or ball hole or part level incompleteness. And although they have a very good results for the in-domain data, they inevitably bring about three shortcomings. The first one will be those methods that is trained in one domain, they actually do not generalize well to the other domain. Okay, so secondly, it's very difficult for real-world partial scans to have ground truth. For example, in KT, we normally do not have a complete shapes. Okay, and because of the domain generalization problem, actually we do not we cannot train on this real-world data and do not generalize well on this data. And another disadvantage is basically these basically discriminative methods, they actually only give one complete shape given a particular partial shape. But in many cases, we're having, for example, ambiguity. For example, if I look at this chair, then actually this chair can be the bottom part can be like a office chair or can be a dining chair, right? And without this information, actually I give all other kinds of geometries all make sense. But obviously, these supervised methods, they do not have this capability to do so. Okay, so then this comes with the performance overview for our performance. This is just a teaser figure for my paper. Basically, with a single pre-trained model, what we can achieve is we can generalize well on all different scenarios, all different domains, including virtual scan or borehole scan, part level incompleteness. And take note that when actually we are pre-trained in ShapeNet, but we can generalize to all kinds of data sets and domains, including ShapeNet, PartNet, and even real-world scans, for example, KT, Metapod, and 3DNet. It's worth noting that even KT, Metapod, and ScanNet, they are from different totally domains, although they are deemed as real-world scans together, okay? And additionally, our framework is able to give multiple reasonable outputs when it comes to ambiguity in the partial input. For example, this lamp, and we do not know the head of the lamp, and then actually this can be of many forms, many forms of the head. Okay, and as well for the airplanes that we can have different types of geometries, and I believe all these outputs are reasonable, but just because there are ambiguity inside the input data. Okay, and how it is achieved, how we achieve such generalization ability as well as the multiple input. Not to mention later, I will show you the editability for particular shapes. Okay, and so this is a basic framework for our method. We call it shape inversion because we're doing shape completion, and this is the first time that we apply GAN inversion into the 3D domain. Okay, so because this method is so different from existing frameworks, it can be a little bit counterintuitive. So let me briefly talk about GAN and GAN inversion, and then slowly introduce this framework. So I believe many of you will be very familiar with generative adversarial networks, or GAN. So basically we have a two-party, the generator and discriminator. So the generator will be taken into a noise of Z and generate, for example, images in the 2D domain or point clouds in the 3D domain. And that the discriminator will be trying to take both the fake one that you generated from the GAN and also the real one from the data set, and to try to discriminate whether it's real or fake. So this is basically a two-party game. And we believe that, or the academia believe that a pretty well-trained GAN, basically the generator can contain a lot of prior knowledge that we need. For example, in the 3D domain, we have 3D semantic info and the geometry details. All these can be actually stored by the generator, which is pre-trained during the two-party thing. Okay, and as for GAN inversion, okay, so for GAN, where the input is a latent code Z, is basically a noise, and then output will be an image or the 3D point cloud, right? Whereas the GAN inversion actually is doing the invert thing. So basically, given an image or given a 3D point cloud, we look for the Z such that we can reconstruct the image or the point cloud, and such that we can minimize the distance between the generated one and the input. So as for now, I believe you could be get a glimpse on how this framework works. So in the shape inversion, in the shape completion task, where we have X in, basically the input, the partial input, right? And what we need to do is basically to give a complete shape over here, XC. And our goal is actually to find a latent space Z over here. Let me use a laser. Okay, a laser point. So basically, what we need to do is basically find a latent code Z such that we generated the complete shape XC, which is as close as to the X input as possible. But since we have because we need to compare the complete shape and the partial shape, right? Then we additionally introduce the degradation module. Basically, we convert our generated complete shape XC into a partial shape XP, and then compare these two shapes. Compare these two shapes using some distance matrix over here we use the transfer distance, which is very popular in point cloud distance measurement. As well, we use the feature distance, where the feature is actually extract from the paired discriminator, which are during the pre-training stage, where we trained the generator and the discriminator. Okay, and once we have these two losses, we add these two losses together, and then back propagate so that we can have the gradient of dz and d theta, so that we can fine-tune the latent space as well as the parameter in the pre-training GAN, so that we can minimize these two distances. Okay, again, this is so different from existing methods, where in existing methods, both the training stage and the test stage, actually they use the same framework, but just in the training they have the backward, and in the test they do not have the backward, but they are using the same network architecture. But over here we have a pre-train stage and the test time stage. So in the pre-train stage, basically we just train the GAN as per normal. And in the test stage, we're actually doing this sort of test stage optimization stuff, which is present over here. Well, this thing is not novel in terms of this framework. And actually in 2D task, for example, a 2D image in painting or 2D image colorization, it has been quite mature. But the key challenge in the 3D domain is actually we basically need to address the intrinsic challenges, basically the unstructured or unordered nature of point clouds, because unlike the image where we have a grid of RGB values, everything is just fixed nicely. But in point clouds, we just have a list of XYZ coordinates, right? And in the two coordinates within 2 point clouds, actually the correspondences is not the same. And talking about unstructured or ordered, one of the major challenges is actually the point cloud uniformity. When we're using a network to generate a complete shape, for example, a chair, if you look at this image, where we adapt the tree GAN, which is the startup back then in 2019. So basically, this is a tree structure generative network. The generator consists of 7 layers of a tree structure, and each layer they have a upsampling stage. So from a latent code 1 node, after 7 layers, they will have 2048 point coordinates, 2048 XYZs. Okay, and we group them in the second last layer. So where we have 32 branches. Okay, and suppose each of the 32 branches, the points should be quite related. I mean, the XYZ value should be quite related to each other, right? And we visualize these branches using these colorful point clouds. So you can see that most of the branches, more than half of the branches, actually focus on the intersection of different parts of the geometric center of the chair, right? And if you count the number of points over here, out of these 2,000 points, around 2,000 points, we actually have nearly 1,000, which is cluttered over here. And this is very unhealthy when we want to represent the detailed geometry of object, because more points centered from a certain parts, there will be less points focused on the other, and will be having less points to represent the geometric details of other parts. And this will be also demonstrating the reconstruction as well. So this is a problem that we need to solve so to make sure that the generative model can generate very uniformly distributed point clouds without sacrificing the fidelity. Okay, so in view of this, what we need to do is to basically come up with a loss to basically regularize the density variance between different local patches around the object surface. Okay, so what we do is we randomly sample, for example, we randomly sample 200 or 100 local patches, and we compute the density. We compute the density for each of the patch, and then we minimize the variance, so that in this way we're actually trying to uniform. We're actually achieve the uniformity of the generated shape. Okay, and how we do this is basically for within each of the patch we have k points, and we just measure the average distance between the center of the patch and the surrounding k points, and we take this as density and measure the variance of these densities among, for example, the 100 patches, and then we just trying to minimize these patches variance, which we call intuitively we call patch variance. And in this way, we can actually achieve uniformity across different structures. For example, thin structure, for example, chair or airplanes, and coarse structure, for example, we have coach and sofa, and also like cars. Okay, and so this is the first key component in our framework during pre-training stage. And another thing is the degradation, right? So let's do some analogy for image imprinting. Again, for the GAN inversion with GAN image imprinting task, where the mask is actually straightforward, because all the pixels are actually aligned by just the coordinates in the grid, right? And whereas in 3D data point clouds, we do not have this luxury. Every points within one point set or one shape, and compared to the points within another, actually their correspondence is first not straightforward, and sometimes ambiguity and can be dynamic, because while we are updating the shape, actually we are changing the geometric positions of XC and XT. Well, of course, we fix the X in. So in view of this, we come up with another important module, which is which we call K-mask. Okay, and before we talk about the K-mask, let's have some intuitive designs. So let's again go back to the 2D level image imprinting. So every pixel is aligned to its corresponding coordinates. Okay, and we can extend from 2D to 3D scenario. So in 2D we have pixel, and then in 3D we have voxel. For example, if we have a voxel with resolution of 32 times 32 times 32 for all these 3 dimensions, right? And for the X input, we voxelize the partial input X in, and then we have the occupancy for each of the voxels, right? And then with this mask, where zero means nothing inside this voxel, and 1 means we do have some points inside this voxel, right? And we can simply have this voxel mask to degrade a certain generated complete shape XC, right? And with this, then probably we can have very sparse output in figure FO here. Okay, which means if let's say we have very how to say high resolution voxels, then even the corresponding regions of the chair, for example, the chair legs, then actually is all filtered out, because we have two precise voxels. But if let's say we downgrade the voxel resolution, then we have only 10 times 10 times 10 voxels. Then what do we have? Of course, the leg will be left, right? But if let's say this the chair back regions, we only supposed to have very little points, but here left more, because we have two two cars voxels, right? So it's always a game between the robustness and the accuracy, right? And then this is just a voxel mask, which directly leverage from the 2D pixel mask, right? And then we can further improve it with a tau mask. Tau basically is a threshold. So for each point, instead of using the voxelization, right, and maybe we can have a more fine-grained mask for each of the points in X in. Okay, then we look for its corresponding points based on a predefined threshold tau. For example, when we take a tau as a 0.03, right? Then actually for each point we just look at those regions that is supposed to leave, right? Then we have the tau mask. After the tau mask, then we have very a lot of regions are filtered out accidentally, right? And the same logic, maybe we can have a larger distance threshold. We make a larger tau. Then this issue happens again, compared similar to the voxel mask, right? It seems the accuracy and robustness thing still exist. And how we can have achieve both the accuracy and robustness, actually, as well as the dynamic stuff, because we need to keep the mask active and updating while we change the XC, right? And how we can do this is we can basically have a fine-grained mask for each point pi in the shape X in the partial input. We just simply look for its k nearest neighbors in the counterpart XC. So we note as the function nkxc here. So for each points pi in X in, we look for its k nearest neighbors in the counterparts in the XC. Then actually we have k times, for example, 2000 points, and many of the points are actually repeated. So what we do is basically we take the union of these points, right? Then we have the partial output XP. So you may note that actually this is not masked. It's actually just a union. We take what we want rather than we filter out what we do not want. Okay, and because we do not use a predefined threshold or voxel, and actually what we do is trying to use the nearest neighbor, and this is very robust and both accurate. And we do every round of backward. So basically this is dynamic as well. And we can achieve very good results if later we see in this table. Okay, so this is basically the ablation study. We ablate both the pre-training stage and the inversion stage. So in the pre-training stage, we compare the introduced patch variance module against the other uniform losses in point cloud completion, as well as the point cloud upsampling works. So you can see qualitatively, the uniformity has been significantly improved. And actually, we do have the quantitative results in terms of minimum matching distance. It has been improving a few times better. Okay, and during the inversion stage, we ablate two things. The first thing is whether the mask can help. For example, if we replace the K mask with voxel mask or the tau mask, then actually we see a significant performance drop compared to our current results, right? And if we look at the another design feature, which is basically the feature distance over here, compared to those only using the transfer distance, our feature distance actually can give more semantic information and hence further improve the performance. And specifically, if we drop the feature distance module, and then we have again, a noticeable performance drop. Okay, so this is just an ablation study to showcase the effectiveness of our proposed modules, right? And now it comes with compare with the SOTAs. The most common benchmark is the virtual scan benchmark, which is designed, derived from a ShapeNet. So commonly we use 8 major categories: plane, cabinet, car, chair, lamp, sofa, table, and boat. So basically they cover majority of the indoor and outdoor stuff. But again, these are just synthetic data. Okay, and so we categorize the methods in terms of supervision signal. Ours, and compared to the other unsupervised methods, actually they are unsupervised, and the rest are supervised methods. So you can see that while we are comparable with the existing supervised methods, we outperform the unsupervised SOTA by a significant margin if you compare with the average and across every different category, right? In terms of CD, which we scale up by 10 times, as well as the, I think this is AP, yeah. I mean, F1 score between the precision and recall. Okay, other than that, we showcase the performance on real-world scans. So because existing supervised methods, all these supervised methods, they do not generalize well on real data. So all here we only compare with PCL to PCL, which is the SOTA for unsupervised methods. And you may notice that although the PCL to PCL can have quite recognizable complete shapes, for example, they can output reasonable chairs or tables or cars in most of cases. But the thing is, in many cases, they do not give faithful results. For example, over here, they have a round tabletop over here, but the PCL to PCL will accidentally give a square one. So because the PCL to PCL, they use an unpaired training, and it's very difficult for them to give a faithful results. Whereas because ours, we exploit the generative prior, which is learned, captured by a GAN, and then we use the test time optimization, so we can have a better results compared to them. And note that even the PCR is trained with the partial shapes of the real world scan and the complete shapes with ShapeNet point clouds. Even with that, they are not comparable with ours. Whereas ours, we only using a single pre-trained model. So basically, they have more leverage on the new data. Okay, and another thing we would like to showcase is the cross-domain validation. So what do we mean by a cross-domain validation? In the TISA figure, you may notice that different methods, they are particularly trained for certain domain data. Okay, for example, virtual scan or ball hold and part level incompleteness, right? Which we domain, the results which we denote in domain results are using the green colors to showcase. And whereas the out of domain results are in purple. So basically, for example, this CRN model. So let's look at this CRN model, this column. They are trained in virtual scan, right? And the performance in virtual scan is good. But they are not trained with ball hold and partnet. So the performance for these two domains, actually they perform very badly, right? And relatively, the PCL to PCL has a reasonable results, even they trained with virtual scan, but still not faithful enough when it comes to different or specific geometries. And in comparison, this is our performance. We constantly give reasonable and high fidelity results whenever we have different domains of inputs, right? Basically meaning that our degradation module as well as the generative network is invariant to these changes. Okay, then it comes to multiple valid outputs. Okay, so given one single output, we can actually output as many outputs as we like. And how we do this is basically, if you look at this framework, actually we can do this inversion stage multiple times sequentially or either parallelly. For example, I want 50 outputs, then we start with 50 latent space instead of 1, right? And then we just we can also improve the mutual distance between different outputs by trying to maximize the difference between different latent space. And actually, we can all tuning how much fidelity we want and how much diversity we want. Okay, and what's more we can offer is actually the editability or shape manipulation, right? For example, if you give me a certain airplane, how about I want something slightly different, right? And what we can do is actually we can first do reconstruction. Then basically when we do reconstruction, we do not have this degradation module as well. When we do degradation, we just omit part over here, right? Because the axion is a complete shape, right? And then after the degradation, we figure out the latent space that is corresponds to a certain complete shape over here, right? And then if we want to do jittering, we can just simply jitter from here. Because the latent space is very compact and has very good semantic information, so all this latent jittering within the latent space will still resulting in plausible shapes, right? So with this, we can have we're actually creating new shapes, right? Given a single input. Okay, then how about if you give me two different chairs, right? Then I want to do morphing or interpolation between these two shapes. The similar logic, we reconstruct target A and target B separately, and then we have two latent space, both for target A and target B. And then we can basically do interpolation in the latent space. For example, weighted average, and then we can have this interpolated between A and B, and we can have very smooth transition between geometric A and geometric B, right? So this comes to the conclusion, and shape inversion actually is the first to apply GAN inversion to the 3D shape completion, and we achieve this by addressing the intrinsic challenges due to the unstructured and other nature of 3D data, so that we can fully exploit the prior captured by a prescient GAN, right? And we further demonstrate a remarkable generalization ability given robust results for both real-world scans and partial inputs of different domains and different incompleteness levels. And of course, this framework is just the first and is far from perfect, and we still have a lot more to further exploring during the future work. For example, the current networks are actually they are trained by a single class. So for example, over here, when we're doing different categories, we actually have 8 different distinct prediction models. And this is a current limitation of all existing generative models. I think this can be further improved. And as another area we can work on is the current shape compilation actually only focus on the input shape which is at the canonical frame. Basically, the pose of the partial input is actually all aligned to a canonical pose, right? And if we really want to solve some real-world data, for example, we want to solve the KT without do some alignment, and I think a lot more work need to be done. And I believe this work, when Shapelnversion, which exploit this GAN parameter for that is trained in synthetic data, I think these ideas can be further extended to work on these ideas, to work on these scenarios. And that's the end of my presentation. And I'd like to, I'm open for any question on this. And by the way, this is just a project page and code so that you can access and give a star. Yeah.
So we have a question from Alex. Alex, I think go ahead and ask yourself.
Yeah, thank you. Thanks a lot for the talk. So I have a few questions. So first, as you said, that the real point cloud data is much more complex and complicated. So if I understand correctly, you use the point clouds of the objects, of single objects that doesn't contain ground, that doesn't contain noise, other objects. How to extract actually the stuff that you want to complete from the real point cloud? You have the LiDAR on the car, and you have huge point cloud of the stand around you, and you want to understand that there is some object somewhere there that you want to complete. How to do it?
Okay, so we follow the PCL to PCL where we use a standalone, well-segmented point clouds, and the framework. I mean, the camera pose has also been aligned as well. Okay, and I believe doing the segmentation is one of the thing. Yeah, so I believe in the future there will be some framework that they can do segmentation and shape completion end to end. Yeah, and in terms of the number of points for example, KT, I believe in many shapes the number of points range from a few hundred to maybe 10,000. Yeah, and actually our framework is quite robust in terms of a number of points. We can, because we can just do we can actually do two things. First, we do some downsample using the furthest point downsample FPS. Okay, so and to downsample to a certain range if the density is quite a lot. Another thing we can do, instead of doing downsample, we can actually tuning the number of K when we using the K mask. Okay, so that we can make sure that the XP and XIN are quite comparable in terms of the resolution. Yeah.
Okay, thanks. So that answers the question. So two more. First, the second very short one. Do you send the label to the network, or it's only point cloud? So do you say that it is a chair, this is an airplane and a point cloud, or only point cloud? Okay,
so we train the GAN using a certain category for each time. So basically, if we want to train chair, then all the complete shapes are chair. But instead of existing methods who are trained using pair data, they have both the partial and complete pairs. In here we only have the complete shape. When we are doing
so you don't mix different objects in one data set, right?
No, because this is because the capability of current SOTA generative models, they only can handle a certain category well. Even though TreeGAN over here, even though TreeGAN claim to perform a multi-class generative model well, but actually in terms of performance, they are 4 times worse compared to a single class one. Yeah, perfect. And I believe with the further advancement in the future for 3D generative models, I think this can be further improved. Yeah, and we can do some further additional TreeGAN as well, maybe. Yeah.
And the last, what practical applications do you see for autonomous driving? So how it can be used now?
I would say it's quite limited because you would need to recognize whether it's a car first and then you do completion, and for pedestrians as well. But if let's say we do not concern about this, maybe if let's say when we have some scenarios that we concern about the dimension or the shape, then maybe this is the scenario. For example, I'm just using my imagination for the indoor robotics navigation, where some of the, for example, some of the furnitures are important for the robotic arms or the robotic vacuum. Maybe this is something that is needed. Yeah. But in order to be used in the real life applications, I think point cloud completion has a far way to go. Yeah.
Thank you.
Thanks.
Any more questions, anybody? If there are none, we will wrap this up. So Genjo, Zoneng, you guys have any closing remarks? Otherwise, I will really wrap this up.
Sure. Anything you want to add up? Yeah. Okay. So this is really a great time to having us here. Yeah. And thank you very much. I'm not sure what's your time zone, and I really appreciate your time. Yeah.
I'm also not sure what's the time zone right now.
Yeah. It's really good time. We really appreciate the discussions and comments over here.
Yeah, friends, thank you so much for this. It took us a while, I think, to set up this time in the event, but it turned out very well, so I'm happy for that.
Yeah.
Thank you.
We really look forward for more sharings if they have new works. Yeah,
for sure. So this is a good chance to say, please keep in touch once you do have some more work that you would like to share. And also, if you're familiar with anybody else who would like to give us talk about an interesting subject in our field, just send them my way. I'm always looking for good people to.
Sure, it's really good, and we will consider that. I will speak with my colleagues and PhD fellows.
Perfect.
Yes.
Perfect. I will say with this for everybody, thank you for joining. Good morning, good evening, good day, wherever you are. This again is recorded, will be posted on YouTube. Everything will be published. Probably will take me a week to prepare all, but that will happen. And thank you again, friends, for this talk. And I will say bye.
Bye-bye.
Thank you. Bye-bye.